Hello students, in this video we'll discuss the gamma function. Let's define a function gamma which maps 0 plus infinity into r by the relationship gamma of x is the integral from 0 to infinity of t to the x minus 1 e to the negative t dt. Okay? So of course, we can make some observations about this function over here. And so the first observation to make is let's plug in some simple values to get a sense of what's going on here. So I plug in, for example, gamma of 1. So gamma of 1 we know is just going to be the integral from 0 to infinity of just is going to cancel out. I'm just going to have e to the negative t, e to the negative t dt. And we know this is negative e to the negative t from 0 to infinity, which just gives me 1. So gamma of 1 is equal to 1. Now the neat thing about gamma is that it's an extension of the factorial function. So what we'll do is this. Let's notice that if I pick n an integer for n and n, let's look at gamma of n plus 1. Gamma of n plus 1 will be the integral from 0 to infinity of t to the, if I have n plus 1 here, that n plus 1 minus 1 is going to turn into an n, so t to the n, e to the negative t, and for those of us who know some probability theory, these come from moments of exponential random variables. Okay, and so what will this be? So I'm going to integrate this by parts. We only need to do this trick one time. This is going to be my u, this is going to be my dv. So if we integrate this by parts, what will happen? I'm going to have u times v, so it's going to be a negative t to the n, and then e to the negative t from t goes from 0 to infinity, minus the integral from 0 to infinity of v du. So that's going to be a n t to the n minus 1, and then what? And then e to the negative t, negative e to the negative t dt. Okay. Now, of course, those limits are 0 if n is greater than 0, because if I plug in infinity to e to the negative t, that's going to dominate the polynomial. And if I plug in 0 to t, I get that the t will be 0. So those boundary limits are 0. I have two negatives over here. Those negatives will turn to a positive. And so what we see here is I see that this is going to be n, just gamma of n. So this is going to be n, gamma of n. So we've just built a recursion relationship. In fact, this relationship is true. This argument generalizes for any x greater than 0, right? In fact, I can say, in particular, that what this shows over here is this shows that gamma of x plus 1 is x gamma of x if x is greater than 0, right? So that relationship is valid for all x greater than 0. Great. In particular, what does this tell me? This tells me that gamma of x is gamma of x plus 1 over x, right, if x is greater than 0. So we're going to come back to that in a moment over here. What this tells me for n and n is that gamma of n plus 1 is n gamma of n, which is n times n minus 1, gamma of n minus 1, using the relationship again. And I can run this all the way down to when I get a gamma of 1 over here. So I'm going to have n times n minus 1, all the way down to 3, then a 2, then a 1, gamma of 1, and we found that gamma of 1 was equal to 1. So what this is exactly just n factorial. So we've derived the relationship that gamma of n plus 1 is n factorial. That's the first thing we know about gamma. Now, as it stands, I've only been able to define gamma for the values that are between 0 and infinity. I'd like to figure out how to kind of extend gamma. So the extension of gamma to the whole real line. So how do we extend gamma to the real line? Before we do that, let's make one observation. This relationship over here gives me a limit, right? So this tells me that gamma of x is gamma of x plus 1 over x, right? And so if I take, we can note, of course, that this is going to be, this clearly is a continuous function of x for x greater than 0 just by passing the limit into the integral over here. But what this tells me is that it's telling me the limit as x approaches 0 from the right of gamma of x is the limit as x approaches 0 from the right of gamma of x plus 1 over x, like so. And of course, what's happening is this is the numerator is approaching gamma of 1, which should not be 1. The denominator is approaching infinity. So this is approaching positive infinity over here. So we have approached positive infinity. So what we can write sort of symbolically is that gamma of 0 plus, that limit is positive infinity. So it's going to diverge. So in other words, if we were to take a look at the graph of this function over here, the graph of this function will look something like this. So here's the positive real axis. There's x, and there's the gamma of x-axis. As we go to 0, it's going to look something like this. That's what the graph of gamma looks like over here. And of course, this is going to correspond to a value of 1 over here, like so. That's what the graph of gamma looks like. Excellent. So now, how do we extend this notion of gamma? Well, what we can do over here is I can say, I can plug in values of x between negative 1 and 1. That makes perfect sense over here. So define gamma mapping -1 up to 0 to r by gamma on these values of x. So for y in this range, if y is over here, so if my value y is over here, gamma of y is going to be gamma, the ordinary gamma of y plus 1 over what? Over y. Now, if y is between -1 and 0, then this makes perfect sense over here. And likewise, if y is between -1 and 0, this number y plus 1 is between 0 and 1. And I know that gamma is defined over there. So this allows me to extend gamma between -1 and 0. And then similarly, what we can do is we can do the same sort of trick. If I wanted to do between -2 and 2, what I could do is the following. I could say, okay, well, notice now that gamma of y plus 2 is going to be y plus 1, 1 less, y plus 1, gamma of y plus 1, which is y plus 1 times y, gamma of y, which allows me to write gamma of y as gamma of y plus 2 over y times y plus 1. And this allows me to define gamma between -2 and -1 by using this formula over here, because this will push that into the right regime. And so in general, what can we say? In general, the relationship is that I can do this n times, and we can write that gamma of y, gamma of x, is really gamma of x plus n over x times x plus 1 all the way down to x plus n minus 1. And so this allows me to define gamma on the entire real line. Of course, this is not going to be defined at 0, at -1, and -2, and -3 at the negative integers, because the gamma function at 0 is going to positive infinity, so there's going to be asymptotes of this function at those values. So we're going to see there's going to be an oscillation in gamma if we extend this to the negative real line, but this defines the gamma function on the entire real line, except for the values 0, -1, -2, etc., all of the negative integers. Thank you very much.